The launch of NASA's Voyager missions marked the beginning of an extraordinary journey into space, showcasing our ability to observe not just Earth, but also everything in our solar system and beyond. Remarkably, even after 46 years, these remarkable spacecraft continue to provide scientists with new and fascinating data about the cosmos. Despite having a memory 3 million times smaller than that of our smartphones and being over 4 times slower than the fastest 5G internet connections, these incredible probes remain leaders in space exploration. Recently, Voyager 1 made an astonishing discovery in interstellar space, challenging everything we thought we knew about the universe. This finding was so unexpected that researchers are left puzzled. So, what exactly did Voyager 1 uncover, and how does it redefine our understanding of the cosmos? Let's delve into the background of this incredible mission. On September 5, 1977, from Cape Canaveral, Florida, something extraordinary took place. Voyager 1 began its journey into space, launched by the powerful Titan III/Centaur rocket. Just 15 days later, on August 20, 1977, Voyager 2 joined its twin in exploring the universe. Their primary mission was to study the gas giants in our solar system, such as Jupiter and Saturn, along with their moons. However, these space travelers ventured far beyond their initial objectives, breaking numerous records on their remarkable journey. They have traveled longer and farther from Earth than any other human-made object, even entering a region known as interstellar space, uncharted territory that had never been explored before. Now over 12 billion miles from Earth, the Voyager spacecraft continued to amaze scientists with their incredible findings. Recently, they made an unexpected discovery that took everyone by surprise. The twin Voyager probes have accomplished incredible feats over the years, including studying the moons of Jupiter and Saturn. Initially, scientists believed these moons were barren and pockmarked like our own moon, but they discovered that they are actually bustling with activity. Voyager 2 was the first of the twins to fly past Uranus in 1986, and 3 years later, it zoomed past Neptune, the only spacecraft to have done so. As these spacecraft pressed onward in their astounding journey, NASA employed various strategies to ensure their continued operation. By shutting down some non-essential components and heaters to conserve power, these spacecraft are expected to remain functional until around 2030. For the engineers and scientists who have been part of this incredible endeavor, the experience has been a mix of joy and melancholy. After years of hard work, just when they thought the Voyager missions were nearing their end, a stunning revelation emerged from the data transmission. The information sent back by Voyager 1 and its twin has become a treasure trove for researchers, sparking numerous discoveries and reigniting interest in space exploration. The Voyager spacecraft were built with meticulous attention to detail, equipped with robust instruments to capture clear images and collect data as they traveled through space. Even before reaching the outer planets, they were already sending back breathtaking photographs that astonished scientists. Voyager 1 began transmitting images of Jupiter, even from a distance, and scientists at NASA's Jet Propulsion Laboratory were thrilled to see the swirling clouds and the iconic Great Red Spot. A pivotal moment came when the Voyager probes made a remarkable discovery on Jupiter's moon Io. This moon, significantly larger than Earth's moon, turned out to be the most geologically active body in our entire solar system. Voyager 1's instruments detected unusual signals from Io, and the images captured revealed immense volcanic eruptions, with one of its volcanoes, called Pele, erupting higher than Mount Everest and covering an area nearly the size of France. The Voyager probes collectively took over 33,000 pictures of Jupiter and its moons, showcasing the planet's beauty and the diverse landscapes of its moons. In addition to these extraordinary findings, the Voyager missions uncovered that Jupiter has faint rings, an intriguing discovery that added to Jupiter's allure. Voyager 2 revealed that Europa, one of Jupiter's 53 moons, has a thick ice shell over 60 miles deep, prompting scientists to reconsider the potential for life in these distant icy worlds. As the Voyager probes departed Jupiter, they received a gravitational boost that acted like a powerful kick, propelling them toward Saturn. This gravity assist was crucial, enabling them to escape the Sun's influence and continue their journey into deep space. Voyager 1 and Voyager 2 headed in different directions after this, exploring new territories. Voyager 1 approached Saturn's moon Titan, which is shrouded in a thick orange atmosphere. Researchers became fascinated by Titan's mysteries, delving into its complex chemistry. Meanwhile, Voyager 2 embarked on its own remarkable adventures, flying past Uranus in 1986 and discovering 10 new moons, and then arriving at Neptune 3 years later, revealing astonishing details about this distant ice giant. Voyager 2 even measured winds on Neptune reaching speeds of 1,000 miles per hour, the fastest ever recorded on a planet in our solar system. As the spacecraft came within 2,980 miles of Neptune, it provided us with new and incredible insights about this remote world. Neptune's largest moon, Triton, turned out to be one of the coldest places in our solar system, with temperatures plummeting to a frigid -391 degrees Fahrenheit. Triton also exhibited cryovolcanoes that erupted nitrogen gas and icy materials into its thin atmosphere. These revelations have deepened our understanding of the unique and fascinating characteristics of the planets and moons within our solar system. The solar wind, those located at its farthest particles and magnetic fields emitted by the sun, creates a structure known as the heliosphere, which resembles an expanding balloon surrounding the solar system. This protective bubble is formed by the solar wind and is eventually compressed by the pressure of interstellar matter, resulting in a boundary called the termination shock. The line between our solar system and interstellar space is referred to as the heliopause, which is estimated to be quite distant. Some theories suggest it lies as close as Jupiter, while more precise measurements from 1993 indicate it is about 25 times the distance from Earth to the Sun. Voyager 1 reached this boundary approximately 20 years after these measurements, detecting an increase in plasma density. Voyager 2 crossed into interstellar space in 2018 but found no significant changes in the magnetic field, which was unexpected given theoretical predictions of variations associated with the Sun's 11-year cycle. At that time, the solar wind was at its strongest, testing these hypotheses. As the spacecraft gather real data, scientists are refining their models of how the heliosphere interacts with interstellar space. In simple terms, our Sun has created a hot, ionized zone, which has transitioned into a less ionized region of the universe. This hot zone likely formed after nearby ancient stars exploded in supernovae, heating the surrounding space and influencing nearby particles. Picture it like a coastline where waves and water swirl around. It's a turbulent area with magnetic fields bending and twisting, rather than the smooth representations often depicted by scholars. Despite finding numerous minor variations near the heliopause, the Voyager missions did not observe significant differences in magnetic fields at larger scales. Eventually, these spacecraft will exit this tumultuous region and enter a more stable interstellar magnetic field. The future of these missions holds a bittersweet farewell. Both Voyager probes are still operational, powered by a system that converts heat from plutonium decay into electricity, although the power output is decreasing to around 4 watts per year, putting the team in a state of urgency. Watching the Voyagers explore space is fascinating, but as they continue their journey, we are preparing to say goodbye. The Voyager spacecraft will keep gathering data, even if communication ceases. Voyager 1 is expected to approach Proxima Centauri, our nearest stellar neighbor, in about 16,700 years, while Voyager 2 will reach its destination in about 3,600 years after that. They will continue to orbit the galaxy for billions of years, long after our Sun has faded and the heliosphere has disappeared, all for that tiny pale blue dot we call home. It's as if their grand adventure never truly ends. While the Voyager probes may still exist, they might not be able to send messages back to us. They carry 2 records made of copper, encased in a shiny gold cover and wrapped in aluminum. These records, famously known as the Golden Records, contain encoded information that reflects Earth's culture. There is about an hour and a half of music, including pieces like Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. The records also feature images of children, dolphins, artists, sunsets, and sounds of nature, such as crickets, rain, and a mother kissing her child. When the Voyager probes were launched, then President Jimmy Carter included a message stating, "We are projecting this message into the universe, expressing hope that one day, after we resolve our issues, we might join other civilizations out there." This record serves as a message of hope and goodwill from Earth to the vast and magnificent universe. One key figure in the remarkable story of space exploration was the renowned astronomer Carl Sagan. He played a significant role in the team that captured images for the Voyager mission, determined to take one final set of photographs before shutting down the cameras. These images would serve as a special gift for everyone on Earth, a last glimpse of our home from the vastness of space. Sagan's perseverance paid off, and on Valentine's Day in 1990, Voyager 1 turned its camera back towards the inner solar system, capturing 60 stunning images. The most famous of these is known as the pale blue dot, taken from a staggering distance of 3.8 billion miles. It remains the farthest image ever captured of our planet, depicting Earth as a tiny pale blue speck in the immense cosmos. Even after 40 years, these spacecraft continue their journey through space, sending back invaluable data from the most remote reaches of the universe. Interestingly, the Voyager probes still rely on old 8-track tape systems for data storage. Yes, you read that right, 8-track tapes, which were all the rage in the 1970s, are still doing the job. This choice reflects the brilliance of the engineers who designed the mission. They needed a robust and reliable medium to store critical scientific data about planets, moons, and the vast spaces between stars. These tapes contain answers to some of the greatest mysteries of the universe. The Voyager spacecraft faced extreme conditions, such as scorching heat, frigid cold, radiation, and the vacuum of space. Remarkably, they not only survived these challenges but thrived, akin to sending your grandparents on an adventurous expedition to Antarctica. What contributed to the success of the Voyager missions? A significant factor was the clever use of gravity assist maneuvers. Think of it as a cosmic ballet where Voyager 1 and Voyager 2 were on a mission to explore the farthest corners of our solar system. To reach these distant locations and gather crucial data, they needed more than just their engines. Gravity assists involve a spacecraft using the gravitational pull of a planet to gain speed, much like a slingshot. For example, when Voyager 1 approached Jupiter, a massive gas giant, the skilled minds at NASA's Jet Propulsion Laboratory ensured that the spacecraft flew past Jupiter at the optimal angle and velocity. Jupiter's gravity pulled Voyager 1, accelerating it as it sped onward, essentially providing a boost. However, executing this maneuver requires meticulous precision. If Voyager 1 had approached Jupiter incorrectly, it could have led to disaster. Fortunately, NASA engineers mastered this technique, allowing the spacecraft to perform a spectacular gravitational dance with the planets. The accuracy involved in these maneuvers is astounding. What's even more impressive is that the team behind the Voyager missions didn't just get it right once. They executed it multiple times. Thanks to these gravity assists, Voyager 1 reached interstellar space, and Voyager 2 followed closely behind. Voyager 2's grand tour of the outer planets also involved gravity assists from both Jupiter and Saturn to propel it toward Uranus and Neptune. Without these slingshot maneuvers, the Voyager missions would not have been nearly as successful. But how did the Voyager spacecraft communicate across such vast distances? Enter the Deep Space Network, DSN, a vital yet unassuming aspect of these missions. Think of the DSN as a vast network of radio antennas located in various parts of the globe, including California, Spain, and Australia. These gigantic dishes, some measuring up to 70 meters in diameter, act like space horns, allowing us to communicate with spacecraft that are far beyond our solar system. Imagine Voyager 1 sending a faint signal back to Earth from the distant reaches of our solar system. When this signal arrives on our planet, it is incredibly weak, but the DSN's massive antennas are prepared to capture it. They lock onto Voyager and translate that signal into usable data for scientists. The DSN doesn't just receive signals. It also transmits commands to the spacecraft. As the mission evolves, researchers and engineers must adjust their plans or instruct the probes on what to do, sending these commands back through the DSN into the void of space. One remarkable feature of the DSN is its round-the-clock operation, constantly listening for those distant signals. It is more than just a collection of antennas. It is the lifeline that keeps the Voyager missions alive, even as the spacecraft venture further into the unknown territories of interstellar space. When we talk about interstellar space, it's crucial to understand that it's more accessible than the farthest reaches of our solar system. Picture the solar system as a vast balloon filled with a haze of comet-like objects held together by the sun's gravity. This cloud of material could extend nearly to the nearest star, and it will take the Voyager spacecraft around 300 more years to approach its edge. Interstellar space begins where our solar system's influence wanes, marking the start of an expansive frontier waiting to be explored.